Hi everyone. Today we're going to talk about special right triangles. Now if you take a look here, we do not have a right triangle, so you may be thinking, what the heck? This is an equilateral triangle, but we can find a way to divide these into right triangles by drawing what's called the altitude. Remember, the altitude is a line that starts at a vertex and drops perpendicular to the opposite side. Perpendicular meaning it makes a right angle, which would then create two right triangles. You may want to write down what an altitude is here. So I'm going to pause the video and write that while you write your own definition. Okay, so an altitude is a line from a vertex to a 90-degree angle to the opposite side. Make sure you have that written down. Okay, so what else do we know about the sides and the angles of the two right triangles here? Well, since this was equilateral, we know that all three of these sides are congruent. We also know that since it's an equilateral triangle, all angles are congruent. So that means they all have to be 60 because all the angles in a triangle add to 180. So 60 plus 60 plus 60 will give us 180. Okay, now since this altitude cuts the triangle in half, that makes both of these angles here 30. So this type of special right triangle is called a 30, 60, 90 right triangle, which is really nice and easy to remember. Math people weren't too creative here. So 30, 60, 90 right triangle, it comes from cutting up an equilateral triangle with an altitude. Let's say that all of these sides are 2 of the equilateral triangle. Then the short leg of the right triangle would have to be 1 because it cuts this base in half here. Okay, so in order to find the relationship between the sides, I first know that the short leg is half the size of the hypotenuse. Okay, so if the short leg is 1, the hypotenuse is 2. If the short leg was 2, the hypotenuse would be 4. If the hypotenuse was 6, the short leg would be 3. You get the idea. I'll do one more maybe just to fill in our chart. Okay, so in order to find the long leg, we can do Pythagorean Theorem to figure out what the relationship is between all 3 sides, not just the 2 here. So if I'm doing a side of 2 and 1, well, we know a squared plus b squared equals c squared, where the hypotenuse is c, and I'll just call the short leg a, and I'll call the long leg b. Again, a and b are interchangeable. You can call this b and this a if you want. So if I do Pythagorean Theorem to figure out what b is, I plug in 1 squared. Don't know what b is, so I'll leave it as b squared. And my long hypotenuse is 2, so I'll put 2 squared. So 1 squared is 1. B squared I don't know yet. 2 squared is 4. Subtract 1 from both sides. You get b squared equals 3. Now, in order to get b by itself, the new step we learned is a square and a square root undo each other. So you take the square root of both sides. That would cancel out the square. So you'd get b equals the square root of 3. And I'm going to leave that as a square root or leave it in its exact form. So if our sides are 1 and 2, our long leg is 3. Okay, let's say our sides are 2 and 4. What would happen? I'm going to do Pythagorean Theorem off to the side. I want you to do it on this case as well. Actually, I'm going to have you on your own complete Pythagorean Theorem like I did up here for sides of 2 and 4, and 3 and 6, and 4 and 8. So you're testing yourself on Pythagorean Theorem, and I'll come back with the answers already done. So please pause the video here. Okay, so here's the case where the short leg is 2 and the hypotenuse is 4. We get b is the square root of 12. But remember, we learned how to simplify this, and we learned this for a reason. This is going to help us develop a relationship here. So I want to break this up into a perfect square. So a perfect square is something like 2 times 2, 3 times 3, 4 times 4. So that's like 4, 9, 25. So which one of those goes into 12? The answer would be 4. So 12 is 4 times 3, which I could then break up into square root of 4 times square root of 3. And the reason I did that was because the square root of 4 can be simplified. The square root of 4 is just equal to 2. So my final answer for the medium-sized leg, or I guess the long leg, but the medium-sized side, would be 2 root 3. Okay, again, I'm going to pause the video and have you do 3 and 4 on your own and check in with me. This time I'm really going to have them both done. Okay, so if you completed Pythagorean Theorem on your own for the last 2 cases, you would have got the long leg is 3 root 3 in exact simplified form, and 4 root 3 in exact simplified form. You can check your work with mine up here. If you want to look at my work for a little bit, pause the video and you can just kind of look at that on your own. Otherwise, I'm not going to go over simplifying any further. I want to actually look at the relationships here. Okay, so the relationship I've noticed is that every single one of these has a root 3. Okay, and specifically, whatever the short leg is the coefficient in front of the root. So like this is 1 root 3, this is 2 root 3, This is 3 root 3. This is 4 root 3. That's craziness, right? So we're noticing some patterns here. And let's go ahead and formalize what this relationship is. If I have a 30, 60, 90 triangle, I'm going to draw off to the side. It looks something like this. It's a right triangle. This is my 60-degree angle, and this is my 30-degree angle, which makes sense because opposite the 30 over here should be the shortest side because it's the shortest angle. That small angle will make a small side. And opposite the 90 is the biggest angle, have the longest side. So my hypotenuse is 2 times the size of my short leg. So let's just call my short leg x. That would make my hypotenuse 2 times the size, so it would be 2x. Then my medium or long leg side, my middle side, is going to be whatever my short leg is times the square root of 3. So my short leg is x. Okay, the opposite the 60, which would be the longest leg, would be x times the square root of 3. So, if these numbers are my x values, this would be x times root 3. Okay, so anytime you have a 30, 60, 90 triangle, I don't need to do Pythagorean theorem. I can just use these relationships to find x and then find the rest of the sides, which is really nice because if I know it's 30, 60, 90 and I only know one side of the triangle, I can still find the other two. Whereas Pythagorean theorem, you have to have 2 sides to find the third. So I'll give you an example here. Let's say you have a triangle. You know it's a 30, 60, 90. So I give you the angles, or you figure out the angles. And let's say this side is, I don't know, 34. Okay, so if I know the hypotenuse is 34, that means 2x equals 34. Because I know my hypotenuse is 2 times my shortest side. So again, x would be the short side. In order to find the short side, I can divide both sides by 2, or divide the long side in half, essentially. So if I divide both sides by 2, I'm going to get x equals 17. So opposite the 30 is my shortest side, or my x side, that would be 17. Then without doing Pythagorean theorem, I know my medium side, or my longest leg, has to be 17 times the square root of 3. And I've not done a whole lot of work. It's a lot quicker than Pythagorean theorem, but this only works on a 30, 60, 90 triangle. Okay, so you'll do more practice with that later. Now, let's say I have a square, and I want to divide this into right triangles. The square already has a 90-degree angle, so if I draw the diagonal, again, a diagonal is a line that connects two vertices. This is the diagonal. Need to know that vocab word. Then I have 2 right triangles here. So if I do that, I have a 90-degree angle, and if this is a square, I know that all 4 sides are congruent. So that means this is an isosceles right triangle, because 2 of the legs here are the same. And if this is a diagonal, that cuts the angles in half here. So if this is a 90-degree angle and I cut that in half, 90 divided by 2 is 45. Okay, so these are 45-degree angles, which we call this special right triangle a 45, 45, 90 right triangle. Again, not too creative with the names, but it's really easy to remember. Okay, so a 45, 45, 90 triangle comes from cutting a square into 2 right triangles. Okay, it looks something like this. You have a right triangle. 2 sides are the same. The angles are 45, 45, and 90. Okay, so let's say one of my sides is 1. The other side would also be 1. Can I find the missing side? The answer is yes, because we know Pythagorean theorem. So let's do a couple cases here. Let's say one leg is 1, then the other leg would be 1, and we'll find the hypotenuse. And let's do another case where one leg is 2, the other leg is 2, and we'll find the hypotenuse. And we'll do a final case, or actually maybe we'll do 2 more cases. Yeah, we'll do one. So let's do a case where one side is 3, the other side is 3, and I have to find my hypotenuse. Okay, so what I want you to do on your own sheet of paper is perform Pythagorean theorem to each of these 3 cases. Case 1, case 2, and case 3 to find the hypotenuse. Okay, so just a little preview of this. If my 2 legs are 1, we know Pythagorean theorem is a squared plus b squared equals c squared. These are my legs. So I'd plug in 1 squared plus 1 squared and find c squared, or find c. I want you to leave them in exact simplified form like we did for 30, 60, 90 triangles. I'm going to have you do all 3 cases on your own. So please pause the video, compute them. It's good practice for a Pythagorean theorem, and I'll come back with the answer. Okay, I've done Pythagorean theorem for all 3 cases. So I color coordinated blue case, red case, purple case up here. Blue case is when the legs are 1. Again, the legs are congruent because it came from a square. If I do Pythagorean theorem, I get 1 plus 1 equals c squared. I take the square to both sides. I get c equals the square root of 2 in exact form. Okay, did the same thing on the sides being 2 and the sides being 3. So for the sides being 2, I'd get c equals the square root of 8. But then I simplify by breaking it up into a perfect square of 4. Square root of 4 is 2, so my final answer is 2 root 2. If I do it on the sides of 3, I get c equals the square root of 18. But simplify that. There's a perfect square that goes into that. It's 9. Square root of 9 is just 3, so I'm left with 3 root 2. Okay, so to fill in my chart here, just kind of notice a pattern. If I had the sides being 1, the hypotenuse was the square root of 2. The sides being 2 each, the hypotenuse was 2 root 2. Then the the legs being 3, my hypotenuse was 3 root 2. So what pattern do you notice here? If the legs are 1, it's 1 root 2. The legs are 2, it's 2 root 2. The legs are 3, it's 3 root 2. So if I call my legs x, then my hypotenuse is whatever my leg is times the square root of 2. Okay, so again, this is just like a 30, 60, 90 right triangle. This will be helpful to finding missing sides with minimal work. And if you only have one side, you can find the other two, which again, you can't do that in Pythagorean theorem. For Pythagorean theorem, you'd have to know 2 sides to find the third. Okay, so I can go ahead and use an example here. Let's say you know that my sides are 500, or I know one side is 500, and I know that this is a 45, 45, 90 right triangle. Well, the first thing you know about a 45, 45 right triangle is I'd be like, oh, it comes from a square, so if one side's 500, so is the other one. And then I know the relationship between this side and my hypotenuse is the leg times root 2. So that would be 500 root 2. And I didn't need to do Pythagorean theorem. It's fairly quick. And also, I only need to know one side to find the other two. I'm going to do one more example. There's a harder case I want to talk about, and this kind of applies to both 30, 60, 90 and 45, 45, 90 triangles. But I'll do a 45, 45 one. Let's say you only know this side. Let's say that this side is 10. And I want to find these sides over here, or I want to find the legs. Okay, so I know that these are the same thing, but I have to figure out what that is. So I'll call those x for now. Okay, now you have an equation for this side, so I'm going to use that equation. I know that this side is represented by x root 2. Okay, this side is also 10. So I could set x root 2 equal to 10, and I can solve for x. So x root 2 equals 10. In order to get x alone, root 2 is just a number. So if these are being multiplied, to undo that, I divide both sides by root 2. Okay, so in order to do that, these would cancel out, and I'd be left with x equals 10 over root 2, which we could go ahead and rationalize, but we're not going to do that for this video. We're going to leave it as 10 over root 2. You don't even have to get a decimal. So again, think of these triangles that I set up here as equations. These sides are just x. This one you'd have to take x and multiply by root 2. Or if you knew this side, you'd set that number equal to that to solve for x. Again, this side is x. This side is x root 3. This is 2x. You can think of those as an equation. So if I knew this side only, I could set it equal to 2x. Or if I knew this side only, let's say you had a 30, 60, 90 triangle. So this is 60, this is 90, this is 30. And I only knew that this side was 10, and I wanted to find these sides. If this is opposite the 60, I know the equation is x root 3 equals 10, because this side, the equation is x root 3. So I divide both sides by root 3. Those would cancel, and I'd get x equals 10 over root 3. Okay, so this side would be 10 over root 3, because that's my x side is opposite the 30. It's the shortest side. And this side would have to be 2 times 10 over root 3, which is just 20 over root 3. Okay, why does this make sense? Opposite the smallest angle should be the smallest side. If I plug 10 divided by root 3 into my calculator, I'll get 5.77, which is definitely smaller than the side opposite the 60, because opposite the 60 is a bigger side because it's a bigger angle. And opposite the 90 should be the biggest side. So if I do 20 divided by the square root of 3, let me try that again, 20 divided by the square root of 3, I'm going to get 11.55, which is longer than the 10. So it makes sense, and you can always check your work by thinking about which one should be longest, which one should be shortest, and then it's a great self-check. So those are our special right triangles.